The maximum matching algorithm is quite straightforward to implement once you've worked out where all the alternating paths are. And that's the main difficulty really, finding the alternating paths. To start with, we just identify a matching. So I'm going to identify B matching up with P, C with Q, and D with T. And that's all I'm going to do to start with. What I'm going to do now is work my way through the process. So the first thing to do is to identify where there are alternating paths. Now an alternating path goes with an unmatched edge to a matched edge to an unmatched edge and so on, and it must finish on an unmatched. So for example, we have this unmatched edge, matched edge, unmatched edge. That's an alternating path. We started at R, which is an unconnected vertex. We ended up with A, which is an unconnected vertex as well, which is what we want. You couldn't, for example, go from D to T along matched, unmatched, matched to P, because we would have started with a matched, finished with a matched as well. We've also finished at a connected vertex and started with a connected vertex. So make sure you always go unmatched, matched, unmatched, matched, and so on, starting and ending at unmatched vertices. So the alternating path that we found went from R to C to Q to A. And it's a good idea to write these things down as you're doing them. So we've got R, C, Q, A as our alternating path. What we do now is we seek to draw the graph again. But what we're doing is we're replacing each of the arcs in that alternating path with their opposite. So if they were unmatched, we're going to match them, and if they were matched, we're going to unmatch them. So first of all, R to C is unmatched in our first matching, so that becomes matched. C to Q is matched, so that becomes unmatched, and Q to A is unmatched, so that becomes matched. We also duplicate any of the matchings that were not affected by our alternating path. So B to P was not affected, so that stays there, and D to T was not affected, so it stays there as well. So we've now got the situation in our bipartite graph where we've got 4 matchings. We have 5 vertices on the left, 5 vertices on the right, and those 2 groups on the bipartite graph. So we would expect there to be a matching which has 5 edges in it. So we're going to seek to repeat the process one more time. So now we look for another alternating path. There are often several different choices for what your alternating path would be. So here I could go from E, unmatched to P, matched to B, unmatched to T, matched to D, and unmatched to S. That would be okay, but it's usually a good idea to try and keep your alternating paths as simple as possible. And on this one, what we could do instead is just go from E to T, T to D, D to S as our simplest alternating path. So writing that one down again, it was E to T to D to S. So that is the alternating path that we're going to seek to replicate, changing the states of the different arcs as we go on to our next graph. So E to T was unmatched, it becomes matched. T to D was matched, it becomes unmatched. D to S was unmatched, it becomes matched. And there we go. We then replicate the ones from the previous graph that were not affected by the alternating path. So C to R, B to P, and A to Q. And we've now got a matching with 5 arcs in it. Since it's a bipartite graph with 5 on the left and 5 on the right, we can't do any better than this. Note that there may be multiple maximum matchings possible. The one that we've got is only one of them. But as long as you're very careful in finding your alternating paths, you should be absolutely fine with this algorithm. The key thing is to be systematic in your search. So once you've identified which are the unconnected vertices, work through them one at a time, choosing each of the different options from that point, and be very careful looking for that alternating path. Other than that, that's this algorithm done.